How many times can you fold a piece of paper? Assume that one had a piece of paper that was very fine, like the kind they typically use to print the Bible. In reality, it seems like a piece of silk. To clarify these ideas, let's say you have a paper that's 1/1000th of a centimeter in thickness. That is 10 to the power of minus 3 centimeters, which equals 0.001 centimeters. Let's also assume that you have a big piece of paper, like a page out of the newspaper. Now, we begin to fold it in half. How many times do you think it could be folded like that? And another question. If you could fold the paper over and over as many times as you wish, say 30 times, what would you imagine the thickness of the paper would be then? Before you move on, I encourage you to actually think about a possible answer to this question. Okay, after we have folded the paper once, it is now 2/1000ths of a centimeter in thickness. If we fold it in half once again, the paper would become 4/1000ths of a centimeter. With every fold we make, the paper doubles in thickness. And if we continue to fold it again and again, always in half, we would confront the following situation after 10 folds. 2 to the power of 10, meaning that you multiply 2 by itself 10 times, is 1024/1000ths of a centimeter, which is a little bit over 1 centimeter. Assume we continue folding the paper in half. What would happen then? If we fold it 17 times, we'll get a thickness of 2 to the power of 17, which is 131 centimeters, and that equals just over 4 feet. If we were able to fold it 25 times, then we would get 2 to the power 25, which is 33,554 centimeters, just over 1,100 feet. That would make it almost as tall as the Empire State Building. It's worthwhile to stop here and reflect for a moment. Folding a paper in half, even a paper as fine as that of the Bible, 25 times, would give us a paper almost a quarter of a mile. What do we learn? This type of growth is called exponential growth. And as you see, just by folding a paper, we can go very far, but very fast too. Summarizing, if you fold a paper 25 times, the thickness is almost a quarter of a mile. 30 times, the thickness reaches 6.5 miles, which is about the average height that planes fly. 40 times, the thickness is nearly 7,000 miles, or the average GPS satellite's orbit. 48 times, the thickness is way over 1 million miles. Now, if you think that the distance between the Earth and the Moon is less than 250,000 miles, then, starting with a piece of Bible paper and folding it 45 times, we get to the Moon. And if we double it one more time, we get back to Earth.
We can multiply 2 by any number, let's say 8, by adding 2 to itself 8 times. The total increases steadily, increasing by 2 at each step. We can raise 2 to the power of any number, let's say 8, by multiplying 2 by itself 8 times. The total increases at an increasing rate, doubling at each step. This is the exponential parent function, f of x equals a times b to the x. A is the initial or the starting quantity. B is how much the last total is multiplied by to get the new total. This is called the common ratio. And x is how many times this repeats. Let's say 3 people each get 2 other people sick with the flu. Each of them in turn get 2 more sick, and so on. In this scenario, A equals 3, the initial number of sick people. B equals 2, the number by which the sick people are multiplied each time the flu is passed on. And X is the number of times the flu is passed on to 2 or more people. So our function is flu of X equals 3 times 2 to the X. When X equals 0, only the first 3 are sick. When X equals 1, 6 more become sick. When X equals 2, 12 more become sick. When X equals 3, 24 more become sick, doubling at each step. This is called exponential growth. Each time a ball bounces, it reaches a height that is proportional to the height of the previous bounce. This proportion is always less than 1, so the ball bounces lower and lower on each successive bounce. This bounce ratio, also called the coefficient of restitution, is the b in our exponential equation, y equals a times b to the x. Just as each bounce of a ball is smaller than the previous bounce, whenever b has a value less than 1, we have exponential decay, where the value decreases or decays over time. You can identify an exponential function from a table of values by comparing successive output values. In other words, is each y value a fixed multiple or ratio of the previous value? Let's look at some examples. Here's a linear function, y equals 3x plus 2. Notice that the y values increase at a constant rate. We're constantly adding 3 to each y value. Here's a quadratic function, y equals x squared. The y values are increasing at a changing rate, going from 0 to 1, then 1 to 4, a difference of 3 or a multiple of 4, 4 to 9, a difference of 5 or a multiple of 9/4, and so on. And finally the exponential, y equals 3 times 2 to the x. Notice that y goes from 3 to 6, which is double, 6 to 12, which is double from 6, 24, which is double of 12, and 48, which is double of 24. One application of exponential functions is in interest and growth rates. Interest is money paid as a fee for using someone else's money. Usually it's a percentage of the amount. This is applied to loans, savings accounts, and various types of investments. Compound interest is when interest is paid based on the current amount, which includes previous interest payments. As a result, interest-bearing accounts grow exponentially. When interest is paid, it is a percentage of the amount currently in the account. So the new amount is the old amount plus the interest, and the interest is equal to rate times the previous amount, the old amount. This is the same as old amount times 1 plus r. If this is done year after year for x years, the amount A in the account that started with principal P, principal being the initial amount, will be as given by that first formula. But banks usually pay interest more often than once a year. They divide the rate r by the number of times per year n that they pay. But since it's paid n times per year, we need to multiply x by n for the total number of times paid in x years. So the compound interest formula is the one shown at the bottom of the page. Here's some examples. Let's say a town of 100,000 people is growing at a rate of 4% per year. How many people will live there in 5 years? Well, this is the same kind of problem as an interest rate problem. We're adding 4% of the current total every year for 5 years. So the new population will be our starting amount, 100,000, times 1 plus r. R is the rate, 4%. We have to convert that to a decimal, which is 0.04. Now we're going to do that 5 times for 5 years. And so we raise 1 plus 0.04 to the 5th power. That gives us a total of 121,665, which would be our estimate for how many people would live in this town 5 years from now. $15,000 is put in a bank account paying 5% annual interest compounded daily. That's 365 times per year. How much is it worth after 3 years? We'll just plug it into the compound interest equation. So our new amount is the principal, the initial amount, $15,000, times 1 plus the rate divided by number of times per year. That's 0.05, same as 5%, divided by 365 times per year, raised to the power of 365 times 3. That's the number of times that it's paid in 3 years. That gives us a total of $17,427.33 after 3 years. Just as investments and savings accounts can grow exponentially, things can also lose value exponentially. Depreciation is the loss of value of an item over time. It's usually figured as a loss of percentage of remaining value each year, kind of like interest in reverse. So instead of 1 plus r, where the value is added, we multiply by 1 minus r, so value is lost. Here's an example, an office copy machine which was purchased for $10,000. Its value depreciates at a rate of 18% per year. How much is it worth after 6 years? We apply the formula, current value equals initial value times 1 minus r to the x, the minus because it's depreciating or declining in value. Plug in the numbers, be sure that 18% is represented as 0.18. And we find out that the copy machine is worth only $3,040.07. Remember to convert your percentage rates to their decimal equivalent r by dividing by 100. Here's a couple of examples for you. Let's look at the graph of f of x equals 2 to the power of x. We see that it has a horizontal asymptote at y equals 0. This is the dashed green arrow along the x-axis. Its domain is all real numbers, so I can plug any value of x into the equation and get a value of y. Its range is all values of y greater than 0. So for any value of x that I plug in, I'm going to get a positive number out. I cannot get a negative number from the parent function. Realize also that graphs of exponentials with other bases look similar. They'll have similar features. They'll just be scaled a little bit differently. Speaking of scaling, let's look at transformations. If we start with the parent function of b to the x, we can end up with a transformed function plus or minus a times b to the power of x minus h plus k. Let's look at what each of these pieces means. A negative sign in front flips the graph, which is a reflection, over the x-axis. If the sign is positive, there's no change. The value of a stretches the graph if a is greater than 1, or compresses it if a is between 0 and 1 in the vertical direction. The value of h shifts the graph horizontally by h units. X plus h shifts to the left, x minus h shifts to the right. Remember that that's backwards from what you might expect, left being negative, right being positive. If it's x plus h, we go left. If it's x minus h, we go right. The value of k shifts the graph vertically by k units. Adding k shifts up, subtracting k shifts down. So in summary, we have exponential functions that look like a times b to the x power. We have growth if b is greater than 1. We have decay if b is between 0 and 1. Remember that b has to be positive, and b is not ever equal to 1. It could be greater or less, but not equal. If we're talking about growth by a rate, which we call r, and this might be the case for interest, population, and so forth, the formula is that the new amount is the initial amount times 1 plus r to the x power. If we're talking about decay by a rate r, this could be depreciation, decay, or other kind of loss, then the new amount is the initial amount times 1 minus r to the x power. Periodic compounding occurs when accounts are paid interest more often than 1 year, so the new amount is the initial amount times 1 plus the rate divided by the number of times per year that it's paid, all of that raised to the power of n, the number of times paid per year, times x, the number of years. The domain of the exponential is all real numbers. I can put any number in for x that I like. The range is going to be all positive numbers. Y is greater than 0. And we have an asymptote at y equals 0. This is the x-axis. And the transformations of the function are as shown on the screen. We have a sign change for reflection, a multiple number a out front for vertical stretch or compression, add or subtract from x for horizontal shift, and add to the entire function value of k for vertical shift up or down.